In this video, we're going to take a brief look at the operators that we've used on sequences over this course. To start off with, we'll take a look at the quantification operators that we have for all and their exists. And then we'll have a look at the specialized operators that we have that can do things like summation, product, frequency, and find the min and max of a sequence. Now, when you look at these operators, what's important to remember about the operators is how they behave over an empty range or for initialization. So what we're really interested in is from an initialization point of view, how do they behave? So how do they behave over an empty range? That's one of the things that's going to be very important. And the second thing then is, how do these operators behave when we are in the loop body, deriving the loop body, and we need to use the split off rule? These two things are very important, and that's what we're going to concentrate on. So the first operator that we'll have a look at is the for all operator. Now the for all operator, you must remember when you're dealing with this operator, for all gives us a conjunction. So that is a set of things that are ANDed together. And that's quite important to remember when dealing with for all. You get a set of statements that are separated by AND. So a conjunction would look something like this. It could be, X and Z and Y and J. That's a conjunction. Any set of statements that are separated by an AND, and they're all separated by AND. So in a conjunction, all it takes is one of these terms to be false, and the whole thing is false. The only way all of this statement is true is if every term in the statement is true. So if we have a look at for all, it's useful to have a look at an actual invariant and see how it behaves. So the invariant that we're going to use just as an example here is for all I greater than 0, less than small n, f.I equal to true. And of course you'd have your other part of your invariant here where you give n a range. So this invariant is really dealing with a Boolean array, and it's checking to see if all the elements in the Boolean array are true. So if we were to initialize our variables here, usually we would initialize our loop counter variable n to 0. Because we want to process all of the elements in the array. So if we initialize n to 0, then of course we're going to get an empty range here. So that would give us an empty range. So I would be greater than or equal to 0 and less than n, and n is 0. So I less than 0 and greater than or equal to 0, that of course is going to give us an empty range. So how does for all operate, or how does it behave over an empty range? Well, if we have an empty range, with a for all, that gives us true. And the reason we do that is because we assume that all of the terms in the conjunction will be satisfied, will be true. We assume that at the beginning. So we assume, if we have a conjunction, we assume that all the terms are true, and then all it takes is one of them to be false and the outcome will be false. So that's an assumption that we make at the beginning of our processing. So if we had a Boolean array, and let's say it was full up like this, let's say it was true, 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 maybe one false, and then another true and another true. we would assume at the beginning of processing to check to see if this contains all true values. We assume at the beginning that it does, and we would initialize to true, and then as soon as we come across a false, it's going to make the whole thing false. So we would initialize whatever variable we're using, in this case all true, we would initialize that to true. And where you're using for all, you have an empty range because you've set n to 0, you would initialize whatever variable you're using. In this case I've just called it all true. You would initialize that to true. For the split off, remember that for all gives us a conjunction. It separates things with an and. So naturally enough, when you go to do the split off, you're going to split off with an and. So if we look at our invariant here, when we go to do the split off part, we would have something like this. We'd have all true would be equal to, for all I greater than 0, and of course when we're splitting off we usually have the +1 bit, and then we have f dot I equal to true, and we split off, so we're splitting off I equal to n, and that gives us all true is equal to, for all I greater than or equal to 0, less than n, and we drop the +1 bit, and we keep the f dot I part over here, f dot I equal to true. And of course normally when we split off we bracket this bit because that's the bit that we're keeping from what we've previously processed. And of course, because it's a conjunction that we're using for all, we split off with an and we split off f dot n equal to true. And of course, we normally say that that follows from our invariant. So let's write that in. So we can say that that follows from our invariant p, that gives us all true is equal to all true and f dot n equal to true. And of course this gives us a nice Boolean expression, and that is essentially the answer to the loop body. That's the statement we'd use in our loop body, along with, n becomes equal to n plus 1. That's where we would have got the +1 bit up here. But without going into a full kind of derivation, just concentrating on the bits that we need. Of course, when we think of for all, we must remember that it gives us a conjunction. It's going to give us a set of things that are ANDed together. When we think of initialization, if we're processing the entire array, of course we're going to set n to 0. That is going to give us an empty range, and we then must look at how the for all operator behaves over an empty range. For all over an empty range, we're going to assume that it's true at the beginning. So whatever variable we're using to store our answer is set to true. And then during the split off, we would split off with an and of course that's going to give us a Boolean expression that's going to be part of the loop body. So it's important to remember these bits of information when you're dealing with the for all operator. The next operator we'll look at is the quantifier there exists. So remember, there exists is kind of pretty much the same as saying there exists at least one. We do have another operator that is kind of the uniqueness operator, but let's concentrate on this one for the moment. So there exists at least one. That's the interpretation of it. And it's often useful to think of a kind of search operation when you think of this operator. So what we're trying to do here in this invariant is to say found is equal to, there exists an I where I is greater than or equal to 0 less than n, f dot I equal to 100. So here we're saying in our invariant that we're dealing with an integer array. Okay, and let's just draw a little array here. So we might have some values in there, 1, 2, 10, 100, 20, maybe 1 again. So we're dealing with an integer array, and we're basically saying, does the value 100 exist in the array, or is there at least one occurrence of 100 in the array? So we say there exists an I greater than 0 less than n, f dot I equal to 100. And of course we have the other bit of our invariant here where we give n a range. So again, we're searching the array, so it makes sense to search the array from the beginning of the array. So the normal kind of course of events would take place here where we initialize I to 0. And if we do that, initialize I to 0, of course we get the usual thing happening here. We get an empty range, because I cannot be greater than or equal to 0 and less than 0 at the same time. So we have an empty range, so you must know how the exists operator behaves over an empty range. Now exists over an empty range so exists over an empty range is equivalent to false. Because, well, a good analogy to remember why exists over an empty range is false is if you have an empty bag and you're asked to search the empty bag for a value or for some item, it can't exist because the bag is empty. So if you've got an empty range and you're dealing with there exists, well then it has to be false. So whatever value or whatever variable you're using to kind of store the outcome of this result, that initially will be set equal to false. And that kind of stands to reason, because most of the time when we're searching for something, we kind of make the assumption that it doesn't exist to begin with, and then if we find it, obviously that contradicts our initial prediction and we set it equal to true. And the other thing to remember, of course, about there exists is that it, in the opposite way to for all, exists gives us a disjunction. So we have a disjunction here. And of course a disjunction is a set of terms that are separated by an or. So something like this, x or y or z or j. That's a disjunction. And when we look at a disjunction of terms, all it takes is one of these terms to be true. And then it doesn't matter what the rest of them are, because it only takes one of them to be true for the whole thing to turn out to be true. That's the nature of a disjunction. And therefore then it makes even more sense to initialize our variable to false, because as soon as we come across one of these terms that are true, as soon as we come across a value in the array that is 100, that will be true, and then the whole thing becomes true and remains true. And that's kind of plain to see when we look at the split off. So from the point of view of a split off, so when we look at the split off for there exists, and what we might have is something like this. We'd have found is equal to there exists an I greater than 0, less than n plus 1, and then we'd have f dot I equal to 100. And if we split off, apply the split off rule, and we're splitting off I equal to n, so that would give us found is equal to, there exists an I greater than 0, less than n, we drop the plus 1, we keep the f dot I here on this side, f dot I equal to 100. And how do we split this off? Well, we normally bracket that because that's what we've previously processed. And because it's a disjunction, we're going to split off with an OR. And we'd have f dot n equal to 100. And of course, it follows from our invariant that that is the same as saying found is equal to found or f dot n equal to 100. And again, that gives us a nice Boolean expression. That's the solution to the loop body. It's just a single Boolean expression in the loop body. Found will originally be false. As soon as we come across an f dot n that's equal to 100, found will become true and will remain true then for the remainder of the processing. So when we look at the exists operator, again, what are the important things to remember? Well, the important thing to remember is that it gives you a disjunction, so you must immediately think of OR. The other thing to remember is that over an empty range, you're going to start off with a false. So whatever variable that you're using to store your answer, along with this operator, you're going to initialize that to false. And that is because we assume that the value does not exist, and also if it's an empty range, there are no values in the empty range, so how can it exist in the first place? So setting it equal to false makes sense. Also, it makes sense because it's a disjunction. As soon as you come across a true, in other words, you find maybe the value 100 in the array, one of those terms is going to become true and it will set it to true for the rest of the processing. The other important thing to remember in terms of the split off is that we split off with an OR. And again, that is because there exists is really just a disjunction. So the next operator we'll look at is summation. Summation is a handy operator for just summing the items in a sequence. And again, we're going to look at it in terms of how we initialize using summation and how it behaves in the split off. So again, if we wanted to kind of show an example of how this operator works, we can imagine an integer array and it's full of values. Let's say 1, 2, 3, 1, 2, 1. And let's say we want to sum those values up. So normally what we do when we're summing things is we start at 0. So it makes sense in this case also to start at 0. And because we want to process all of the elements in the array, we want to get the total sum, not just the sum of some elements in the array, but the sum of all the elements in the array. We would of course start our processing at 0 and then work towards n. So once again, we're in a situation where it makes sense in this case to initialize n to 0. So we initialize n to 0. And then, of course, that gives us the usual thing happening down here. It gives us an empty range at the beginning in our invariant, because I greater than or equal to 0 less than n, where n is 0, is an empty range. So how does sum behave over an empty range? Well, if we have an empty range to begin with, if we've no elements to process, In other words, think of that empty bag again. Add up the values in an empty bag. Well, if there are no values in the empty bag, the sum is 0. There's nothing in the bag. So again, we set sum to 0. So this makes sense because we have an empty range. So we can set sum to 0. And naturally enough, when we're summing, doing any kind of addition, we always start at 0. We don't start our addition at some arbitrary point on the number line. We always start at 0 to get a total. So setting sum to 0 makes perfect sense even from an arithmetic point of view, but from a logical point of view, where we have an empty range, there can be no other value than a sum of 0 over an empty range. So we set sum to 0, set n to 0, and that will work fine for initialization. How about split off? Well, in the split off rule, we're going to use a plus, because essentially what this statement is going to give us, it's going to give us f0 plus f1 plus f2 plus f3 plus f4 plus f5. But we don't calculate that sum all in one go. We could easily write that sum out and calculate the value. But when we're writing a program, we're not doing that calculation all in one step. We're doing it in a piecemeal way. We're doing it in an iterative way. So we take the first value, then add on the second value, we get a total. Then we add on the third value, we get a total. Then we add on the fourth value, we get a total, and so on and so on. So because we're doing it in this incremental way, we need to look at how sum behaves in terms of a split off. So when we look at the split off for sum, so when we split off with a summation operation, we're going to get something like this. So we have sum is equal to plus I greater than or equal to 0, less than n plus 1, of course, because we're splitting off, and we have f dot I. So when we go to split this off, and we would split off I equal to n, so everything up to n, we would have sum is equal to plus I greater than or equal to 0, less than n. We drop the plus 1. We keep the f dot I on this side. And again, that's what we've previously processed in the brackets. And when we split off, we simply just split off with a plus. And we add on f dot n. And of course, that follows from our invariant, because this bit in the brackets is what we've previously processed. So if you can imagine for a moment, if we've processed everything up to this point, 0, 1 and 2, we've added up 1, 2 and 3, which would give us 6. So our total here at this point is 6, and then we're going to add on the 1 part onto the 6. So that's essentially what this is. The bit in the brackets is what we've previously processed, and we're adding on the next bit onto that. So the bit in the brackets, the value for that will have been stored in sum. So again, following from our invariant, what we can really say here is sum is equal to sum plus f dot n. And that gives us our loop body. So sum is pretty straightforward. You've just got to remember that, okay, if you're processing all the elements in the array, you're going to set n equal to 0. You're going to process from the beginning to end. You're also going to set sum equal to 0 for a number of different reasons, because you're going to have an empty range to begin with, and the sum over an empty range is 0. And also, when you start your calculations from an arithmetic point of view, you always start at 0 to calculate a total. And then for the split off, you must remember that it's just a simple addition. You're just adding on the next part to your answer. So this is what you've previously added up, and then you're going to incrementally add on the next bit and the next bit and the next bit. And that is because it's a program. We're doing this in incremental steps using a loop. We don't just calculate it all in one go like we would on paper. We're adding on it. We're adding on each bit at a time, every time around the loop. Now, there is slight variations to summation. For example, you might want to just sum the odd values or sum the even values or sum values greater than 100. And in that case, you would need an if statement. You'd need to bring in case analysis in order to check to see if the value that you're currently processing meets your criteria, and then you would add it to the sum. But this is how summation works in a very basic way from the initialisation point of view and through to the split off. The next operator, of course, is the product operator, and it's similar to sum in that it behaves in the same way. The mechanics of it are the same, but from an initialisation point of view, it's slightly different. So once again, if we just imagine we have an array, let's take a pretty small array this time just for ease of making an example. So we would have 0, 1, 2, and n there. So let's say we wanted to find the product of this array. It just contains the number 2, has 3 occurrences of the number 2. We want to process the entire array, find the product of that array. Well, of course we're going to set n equal to 0 to start our processing at the beginning. And that's going to give us an empty range. So I greater than or equal to 0, less than n. Empty range is a contradiction, but it gives us an empty range. So how does product behave over an empty range? Well, this is tricky because you might initially say, well, product over an empty range is 0. Well, in fact, it's not. It's 1. And the reason for that is because we're dealing with multiplication. If we set product to 0, then everything that we multiply will be 0. And that's because, again, we're doing this in a piecemeal way. So if we set product to 0, we'll end up then multiplying by 0. We'll include a 0 in our multiplication, and everything multiplied by 0 is 0. So we can't do that. We can't set it equal to 0. We must set it equal to 1. Because anything multiplied by 1 is itself. So it's not going to change the value of it. It's just going to be itself. So we'll actually see when we get to the split off how this will work out. It will work out. But it's just important to remember that when you're dealing with product or multiplication, you do not set the product equal to 0. You must set it equal to 1. So for the split off, with product, we'll end up with something like this. So we could have product is equal to product of I greater than or equal to 0, less than n plus 1, and then we'd have f dot I. So when we split off, I equal to n, we'll end up with product is equal to the product of I greater than or equal to 0, less than n, we drop the plus 1, f dot I, And again, look, this is what we've previously processed, so we bracket that off. So how do we split off now? Well, just like we split off with a plus for summation, we're going to split off with multiplication here. And we're just going to multiply on the next bit, the f.n bit. So, for example, in our array up here, let's imagine we had processed everything up to here. Okay, so we've processed f.0, we've processed f.1, and we've multiplied these two values together, and of course that will give us the value 4. And then what we're going to do is multiply on the next value, which is 2. So the f.n bit here is 2. This bit in the brackets here is what we previously processed, which will have a value of 4. And of course, what we've previously processed, the value for that is stored in product from the previous time around the loop. So again, we see that, well, it follows from our invariant, the way our invariant is working, that this really means product is equal to product multiplied by f.n. So you see that in the split off, we split off with the multiplication symbol. We would usually initialize our loop counter variable to 0. That's going to give us our usual empty range. But the most important thing to remember here is that you cannot initialize product to 0. You must initialize it to 1. For example, if we go back to the split off rule, and if we imagine that the first time round the loop and product is 0. So let's imagine product here is 0. So you get product is equal to 0 multiplied by f.n. Well, 0 multiplied by f.n is 0. So product now becomes 0. And it's still 0 the next time round, and whatever the next element is multiplied by 0 will still be 0. So you get this constant multiplication by 0, which will of course end in 0. So we cannot set it to 0. We have to set it to 1. So the first time round the loop, if product is set to 1, what we'll effectively get is product is equal to, product is initialized to 1, so you'll get 1 multiplied by f.n. And 1 multiplied by f.n is f.n. So product will be equal to the first element in the array the first time round the loop, and then we'll multiply on the next bit and the next bit and the next bit incrementally each time around the loop. So that is why it is important to set product, in this case, equal to 1. So just remember, dealing with product or multiplication, you need to initialize to 1, not to 0. N can still be initialized to 0. That's starting the processing at the beginning of the array. That's not a problem. From the split off point of view, it's very similar to the plus, except that you're using multiplication here instead of plus. And of course, it works out in just a simple expression of product equal to product plus f.n. Now this is a simple version of product. As we mentioned with summation, you may want to find the product of even elements, find the product of odd elements, find the product of elements that are greater than 10. There's lots of variations on this that you can do. Once you have a variation on this, like find the product of even, then you're into using case analysis and an if statement to find out whether f.n meets that criteria, and then of course you're just going to multiply across by product multiplied by f.n when you find a case that meets your criteria. The next operator we're going to have a look at is frequency, or sometimes known as cardinality. So frequency is just simply counting the occurrence of something. So when we count the occurrence of something, it's similar to summation, except that we're not summing up the actual values. We're just adding 1 to our frequency every time we find something that meets our criteria. So if we take an example array, and let's say we wanted to find the frequency of elements in the array that are greater than 100. And let's say we fill the array up with some values. So we can see in this array that we actually have two values in there that are greater than 100. We have 101 and we have 200. So just looking at the array straight away, we can see that, well, the frequency of elements that are greater than 100 is 2, because we've got two occurrences of elements that are greater than 100. So that is the frequency. How many times does that particular case occur in the sequence? So once again, if we're processing the entire array, we would usually set n to 0. And that's where it all starts, nearly all of the time. So we set n to 0. And of course, that gives us our empty range here in our invariant. Once we have an empty range, then we need to begin to look at, well, how does our operator behave over an empty range? So frequency over an empty range is 0. Very similar to sum in that case, because if you're given an empty bag and you're asked, what is the frequency of oranges in the empty bag? Well, there are no oranges in the empty bag because it's empty. So it stands to reason then that you would set frequency equal to 0. So cardinality over an empty range is 0. Once we have an empty range, frequency is 0. Frequency of anything over an empty range is 0. So how does the frequency behave then in the split off? So split off for frequency or cardinality, well, it looks a bit like this. So we might have frequency So we would have frequency is equal to cardinality of I greater than or equal to 0, less than n plus 1, because remember we'd be processing the loop body at this point, so it's n plus 1. We would have suggested to increment n by 1 to get to this point, and we have n plus 1 here. And then the term is f dot I greater than 100. So when we split this off, so split off I equal to n, we end up with frequency is equal to cardinality of I greater than or equal to 0, less than n, we drop the plus 1, we keep the f dot I on this side, greater than 100, and remember that's what we've previously processed, so we bracket that off to kind of separate that out. Now how does the split off work here? Well, the split off, it's not just adding something on, it's not just adding the next value on, it's adding 1 on if we have found something that is f dot I greater than 100. So the way we do the split off in this case is we say plus the cardinality of f dot n greater than 100. Okay, now how does this work? What does this mean? Well, the cardinality of true is 1. And the cardinality of false, yeah, you guessed it, is 0. So if f dot n is greater than 100, we're going to end up with true here. And the cardinality of true is 1, so we'll be adding on 1. If f dot n is not greater than 100, we'll have false. The cardinality of false is 0, and we'll be adding on 0, in effect not changing our frequency. So that's how that works. If it's a true, we're adding on a 1. If it's a false, we're adding on a 0. And then that way, depending on the outcome of f.n greater than 100, we'll simply add on a 1 or add on a 0 to our frequency, either incrementing our frequency or just leaving our frequency alone. Now, of course, the next part of this is a case analysis. The only way you will know whether f.n is greater than 100 is to do a case analysis. You can't leave it like this. This isn't the final answer. You then need to go and do a case analysis on f.n to test to see whether it is greater than 100 and either add on 1 or add on 0. This, from a logical point of view, is fine, but we don't have this kind of terminology in our programming language, so we must translate this into case analysis and then into an if statement. It would be nice if we could leave it like that, but the guarded command language doesn't have this notation, so we're forced to translate this into a case analysis. So from the point of view of frequency, what are the important things to remember? Important things to remember are that we initialize to 0, we're finding the frequency of something, counting up how many times something occurs, and in most counting exercises we usually start at 0. When we have an empty range, the frequency over an empty range is 0. That stands to reason, so that's another good reason to set it to 0. In the split off, when we split off with a plus, but we're not just adding on f.n. That doesn't make sense. We don't want to add on the value of f.n. We want to add on a 1 if we found something that meets our criteria, or we want to add on a 0 if not. And the way we express that is we add on, we say plus the cardinality of f.n greater than 100. And remember, cardinality of true is 1, cardinality of false is 0. And that's what gives us this logic that we end up with here. The next operators that we'll look at are the min and max operators. And these are slightly different in that usually when you want to try and find the minimum or the maximum of something, it's a comparison operation. So that's slightly different for a start. The other thing that's different about these operators are we don't actually have a min and max in the guarded command language. So while I'm using it here as part of my invariant, we don't actually have that min or max in the guarded command language. So when we deal with min and max, we actually must rewrite our invariant using a for all. So what I've got here is actually incorrect in terms of an invariant, but it's useful just to kind of have a look at it. So what we have is max I greater than or equal to 0, less than n, f.I, and so on. But this is incorrect because we don't have this as part of the guarded command language. We need to rewrite this. So in fact, if we were to go back to our invariant, or if we were to go back to a post condition that would use min or max, we might have largest is equal to max I greater than 0, less than n, f.I. So that would be a post condition that uses the max operator. Now what we actually have to do with that is we have to rewrite that using a for all. So if we're trying to find the largest, what we would do is we would rewrite it like this. We would say for all I greater than 0, less than n. And then we would say, so if largest is going to be the largest value in the array, we would say f.I is less than or equal to largest. So we're finding the largest, so max being the largest. So then if largest is going to be equal to the largest value in the array, another way to say that is that every f dot I is less than or equal to largest. Now what is largest? That kind of doesn't make sense yet because we don't know what largest is. Largest is some variable. But how we initialize will make sense of this. So what we do is we assume at the very beginning that the first value in the array is the largest. So if we take an array here, we say that's f. And if we say, for example, let's say this is 0, 1, 100, 200, 2. So if that's our array, what we're going to do is we're going to say at the beginning we're going to assume that the first value in the array is the largest. Now plainly this is not the case in our example here, but it's worth assuming at the beginning that this is the largest value in the array. And then what we will do is we will compare every other element as we go. So we're comparing, okay? We're assuming that this is the largest, and then we can compare each other element, and if we find a bigger one, we note it and move on. And that's the way we operate with the max or min. Now max or min is that both of them are rewritten using a for all, but what will be different is, okay, the name of your variable might be different, but also this symbol here will change. So if it was to find the smallest value in the array, well then it would be f dot I, or f dot I would be greater than or equal to smallest, or something like that. So it's really this symbol that changes, and possibly the name of your variable over here. That's what would change depending on whether it's a max operation or a min operation. So what we do here at the beginning is let's write our invariant out as well. So we would say then for an invariant we'd have for all I greater than or equal to 0, less than small n, and then we'd have f dot I less than or equal to largest, and our invariant, oh, let's fix that, that should be small n there. So that's our invariant in full. And then what we're going to do is set largest equal to the first variable in the array, or the first value in the array. So we'd set largest equal to f dot 0. And what we're going to do is we're going to process not from f dot 0. Because we've set largest equal to the first value in the array, we don't want to set n equal to 0. If we set n equal to 0, when we compare the first two elements, we're going to be comparing f dot 0 with f dot 0. So we don't want to do that. We want to set n equal to 1. Because if we set n equal to 1, then we'll be comparing that value with that value. So we'll be comparing f dot 0 with f dot 1. So we'll be comparing using two different values in the array, which makes sense. We'll compare f dot 1 with f dot 0, and then we'll compare f dot 2 with f dot 1, and then we'll compare f dot 3 with f dot 2, and f dot 4 with f dot 3. So this makes sense when we're dealing with a comparison operator like min or max. And there are many examples of this in different problems that we'll come across where we need to compare elements of an array. For example, in a sorting algorithm, we'd need to make comparisons of elements in an array. and we'd use a similar process. So when we go down here, we'll see that setting largest equal to f dot 0 and n equal to 1 will make sense. Now for the split off on this, it's again pretty simple because we're using a for all, and as we know, when we use a for all, we get a conjunction. We get things that are anded together. So, you know, a statement like this where we'd have things that are separated with an and. So when we go to the split off, it's just another simple operation of using a conjunction. So for example, for our split off, we would have for all I greater than or equal to 0, less than n plus 1, we'd have f dot I less than or equal to largest, and then we split off I equal to n, and that gives us for all I greater than or equal to 0, less than n, we drop the plus 1, we're left with f dot I less than or equal to largest, and this is what we've previously processed, and we split off with an and because it's a for all, so we'd have and f dot n less than or equal to largest. And what we have in the brackets here is the largest value that we've processed so far. So largest here is essentially our answer, and largest will have found its value in this set of brackets. So if we've processed everything, say up to this point in the array, let's imagine we've processed everything up to here, the largest value so far would be 1, and largest would have the value of 1, and then we're going to process the next element in the array, which is 100, and we'll compare 100 with 1, and we'll find the next largest and note that and move on. So this set of brackets here is essentially all stored in largest. So when we go to process this or move on from this, we kind of just disregard everything in the brackets. There is kind of already stored in largest so far, and then we just have this bit to deal with. And of course we need a case analysis now, because we need to compare two values with one another. We need to check to see if f dot n is indeed less than or equal to largest, or if it's greater than largest, then of course we need to reset largest, note the new largest value and move on. So the important things to point out about using min and max is, first of all, we can't use min and max as part of an invariant. It's not part of the guarded command language. We must rewrite it in a way that uses the for all symbol. It's absolutely fine to use max in your post condition, but when you go to write your invariant, you must rewrite it with a for all. And once you're dealing with a for all, you're dealing with a conjunction. And the other thing that you just need to be careful of is your initialization. So from an initialization point of view, remember this is a comparison operation, and usually what we do is for smallest or largest or min or max, we assume that the very first value in the sequence or the array is the max or is the min, and then we make our comparisons with the neighboring elements as we move along. And to do that, to make sure we're comparing it with a neighboring element, we don't set n to 0, we set n to 1, so that we're comparing at the very beginning f.0 with f.1.